Why don't we go ahead and get started? So today Z is presenting on his paper on this analysis of structure and dynamics and three neuron motifs. So that should be interesting. Stefan should be joining us momentarily. So why don't we? Well, let me first ask: does anyone have any issues that they need to discuss before we begin the meeting?
The progress is pretty nice.
Okay. How about Jesse? Do you have anything to say before we start? Okay. I guess we can start the paper presentation. If Stefan joins us in the middle, we can just, he can probably ask questions about it. So Z, why don't you start?
Okay. Yeah. I'm going to get started.
Yeah.
So today I'm going to present a paper, Analysis of Structure and Dynamic in Three Neuron Motifs by Cross et. So this paper is going to address a central question as how the dynamics of a neural network is affected. Like what's connection, like what sort of connections, patterns, or what's the weight that can affect the dynamics of the neural networks. So to approach this question, they use three neural motifs and define some very interesting metrics for measuring the differences of neural networks and also the dynamics of the neural network. So firstly, I'm going to define some terms. So first one is a motif class. So a motif class is, to be short, a class of neurons, that class of neural networks of topologically identical structures. So for example, like here, these 6 neural networks has topologically identical structures and they form a motif class. So in this paper, O motif class has 6 neural networks of topologically identical structures, and by permuting the connections, they had more than 3,000 motif classes. And the connection weights are ternary. That means excitatory connections only have weights of 1, and inhibitory that is weights of -1, and if there's no input, that is 1. And the state of the neurons are binary, that is only 0 or 1. And therefore, there can be 8 states, right? Because there's 3 neurons, and by permutation, it's going to be only 8 states. And
Hello?
the column, say column 2 and row 1 of the transition matrix is the probability from state 1 to column 2. Say the basic structure of the network. And then they define 2 kinds of distances. First is structural distance. So look at the examples here. So the structural distance is simply the numbers of different sites between two neural networks. And structural distance of a motif is just the minimum of all of this structural distances. And for dynamical distance, it is the squared sum of the square roots of the sum of the squares of the differences, right? Just as you can see in this equation. So that is dynamical distance. That is very simple. And they basically generate some very interesting results. So they found a positive correlation between the structural distance and dynamical distance, as you can see in the figure. And note that the structural distance is discrete, so therefore it's just like lines here. But the distribution for each structural distance, the distribution of dynamical distance is very wide. All right. So another finding of this paper is the cluster distribution of motive classes. So they basically use multi-dimensional scaling, and therefore to create such plots. So in those plots, each dot represents a motive class, and the distance between two dots is the distance between between the two motive classes. So as you can see, there is nothing very significant between the density and the structural distance or dynamical distance. By the way, density is the fraction of non-zero connections to the all possible connections. And balance indicates the ratio of the excitatory to inhibitory connections. So for the structural distance space, there is a six-fold symmetry, and that's probably because there's only 6 permutations of neural networks in a motive class. And for the most interesting one is the top right, the dynamical space with coloring of balance. So you can see there is a very strong cluster distribution of motive classes. That means the ratio of excitatory inputs to the inhibitory inputs strongly affects the dynamics of the neural networks. And probably it's going to be the effect is going to be more significant than just the structural distance to the effects of the structural distance to dynamical distance. So the paper is simply asked that, and it is very inspiring. So firstly, it lets us to think about how to think about structure and say, for example, the balance, etc., of the neural network before we are designing one. However, the paper also has some drawbacks, some shortages. Sorry. The first one is there's only 3 neurons in a neural network, and also there is the weights are all just ternary and binary. However, increasing all of the three attributes will greatly increase the computational requirements, and therefore can probably take a lot of time to compute, and it's going to be a challenge for this research approach. So one shortage of this paper is that the ternary, the binary states, the ternary weights, and just 3 neurons are actually not actually far less than the practical implementation of neural networks. So for a usefully large neural network, does the finding of this paper still apply to those usefully large neural networks? We are not sure. So that's the shortage of this paper. And this paper also let me remember a paper that is a critique to the I forgot the title of this paper. So let me see. Sorry. can find the title of this paper. It is a critique to the say deep learning, and it is like inspired by animal brains. So animal brains are highly structured when they were born, and therefore when we are designing the neural network, we cannot just choose a very general model. We have to think about structure, and probably for artificial intelligence, maybe evolve from existing successful neural network structure is a better approach than just build a neural network from scratch for deep learning and artificial intelligence. So basically, this paper is relatively easy and very short, and but I choose this paper because it is very inspiring for our learning in neural networks, and for when we are designing the neural networks, say, and also for to let us think about artificial intelligence and deep learning. Yeah. So I'm very sorry that my technical problem. Yeah, that's it.
Oh.
Sorry about that.
No problem. Yeah. So that was an interesting paper. I find it interesting. Like, so I guess people have been sort of interested in animal models for a while. For like, I mean, usually people think about the human case and they think about human brains when they think about designing an artificial intelligence. But there are also animal brains, and there's actually a wide range of nervous systems that one can draw from there. And I guess like even some of the big names like Google and some of the other companies are getting into that space. Although I don't know how successful they'll be, because it's that first of all there's a lot of variation there, and secondly it's really if you look at animal models, it highlights sort of well, what do you mean by intelligence? Is it what attributes are what constitutes intelligent behavior? And there you start to get into things like well, if you're depends on what you want to do. If you want to forage, or if you want to like do some other type of activity, then the nervous system of the animal will be maybe very suited to a specific task. Yeah. So Jesse says there's a cool book about how octopus cephalopods. Let me open up the chat. Octopus cephalopods are another development of intelligence, which is really cool compared to mammals. I've read about 5 pages of it or so and talked about it with some friends, but I'm looking forward to reading the whole thing. Exactly. So octopi are actually very intelligent, and in animal behavior they use it as a model of an intelligent system that isn't really anything like humans. And so but I think some of the points that they raise about like having like different types of setups for how to represent neurons and neural networks. So the idea of having ternary connections and binary states, so you end up with a little bit more variation in terms of the output, or at least you're working with a wider range of representations for things. I think that's interesting. You don't see that very often.
Yeah.
So what do you like? Do you think you could apply this to your work, Ziyi? I mean,
connection lost?
Oh, I don't know what.
Sorry, can you hear me?
Yeah, I can hear you.
Okay. You mean internal connections applied to my
well, I mean,
implementation?
just in general, this paper, could you apply some of the concepts to your?
Yes. Yeah. So this week I was building the association network, association parts of my network. So I took the outputs of the olfactory system that I built, and I just use the raw values of the gas accessory as the inputs. So I make associations between the raw gas accessory stimuli and the processed olfactory stimuli, and the association seems to be sometimes it seems to be very nice, but sometimes it's not. So I guess one problem is that I just let them to have full connections. And hi, Stefan.
Yeah, hello.
Yeah.
Sorry for being late and not home, and the connection there was bad. I had to look for another opportunity.
It's okay.
Yeah.
Yeah. So that was
Okay. Since you're can someone can you mute yourself, Stephen? Okay, thanks. It's like there's an echo sometimes. Since you were able to go through the paper in a relatively short period of time, could you give some of the highlights for Stefan again, just to maybe we can go through it again and get a he might be interested in a couple of the things that
Sure. Let me share my screen again.
Right.
So because I am using hotspot, so I cannot access to Google Slides, so I cannot have my slides, so I can only do my presentation with the raw paper. So the presentation is gonna be a little bit, seems to be a little bit boring and interrupted. Sorry. So yeah. So the highlights, firstly is the motive class. A motive class is simply, is it? Sorry. Stefan? Can you see my screen?
Sure. I hope the presentation now, so you don't see some interrupting sounds.
Okay.
Do not hear it. Okay. Yeah, I can see it quickly. Yeah, sure.
Cool. So motive class is simply the neural networks of topologically identical structures. So for here, it is one example of motive class. So all of these 6 neural networks have topologically identical structures, as you can see. So they have more than 3,000 of motive classes, and it defines two distances. The first one is structure distance. So here, the connections are ternary. So one indicates it is an excitatory connection, and negative one it is inhibitory connection, and 0 is there is no connection.
Oh.
And neural networks, neurons are binary neurons. So so the structure distance is simply that you count the difference in the connections, right, for 2 neural networks from one motive and from another motive, and then the number is just the structural distance between 2 neural network. And the structural distance between 2 motive classes is the minimum of all of the neural networks from the 2 motives. And dynamic distance is taken the state transition matrix, and the state transition matrix is built from the state. So because a neuron is binary, so so one neuron has 2 states, and therefore for 3 neuron class, 3 neuron networks, they will have 8 states, and therefore a transition matrix is just like, for example, the column 2, row 1 of the state transition matrix is the probability for the network to transfer from states 2 to state 1.
Yeah.
Yeah, and the dynamic distance is just summed squared of those differences in the matrix.
Oh, yeah,
And
makes sense.
then, yeah, they just do the statics, and found there is a positive correlation between the structure distance and dynamical distance. And the structure distance is discrete, so it is like some lines here. But the distribution is very wide for each values of structure distance. And then they use multi-dimensional scaling to find the relative distance between the motifs and to map it into a Cartesian space. So, so here each dot is a motif, and the distance between two dots is the distance, the corresponding distance between the two motifs. Density here is the fraction of non-zero connections to the all possible connections, and balance is the ratio of excitatory synapses to the inhibitory synapses. So for density, there's no significant finding here, right? But for balance, the finding is very interesting. So here there's a very clustered distribution of motifs in the dynamic space with balanced coloring. So as we can see here, right? So that indicates that the balance, that is the ratio of excitatory to inhibitory, significantly affects the dynamics of the neural network. And also for the structure space, there is a very significant six-fold rotation symmetry. And that is probably because there is only 6 permutations of connections in the motif class. So as you can see here, so for each motif class, there's 6 permutations. So that's probably the reason that it has a 6-fold rotation symmetry.
Yeah, that could be, yeah. Okay.
Okay, I think he got interrupted a little bit, but so Stefan, do you have any thoughts about that? About what he was showing? I think he'll come back online here in a minute. Hello? Can you hear me, or?
Yeah, I can hear you.
Okay. Oh, did you have any thoughts about that?
I'm sorry, I just hear the playback details. Like, is it some kind of delay or something?
It might be, okay. I think the connection dropped, and he'll be back.
Okay. Yeah, it's a very interesting paper indeed, as it seems. So maybe we could use this like the results they achieved to kind of to assess the neural network motifs that we developed during the project. Also, of course, once Z is back, I have some questions.
Okay.
To him. So.
Yeah, I don't know if he's back or not. Looks like he's trying to come in. Yeah, the connections are kind of. He's on a hotspot, so it's.
Oh yeah.
Yeah. Well, I thought it was an interesting paper. I didn't quite get everything what they were doing, but we were talking before about how it's kind of expands the sort of the typical neural network, like in terms of thinking about motifs and thinking about different types of, generating different types of signals. So you have, ternary states, and then ternary connections and binary states. So you have a larger number of possible, states to work with, and then you have a larger number of greater variety of outputs. And then we also talked a little bit about animal models and how in animals you have very different nervous systems than say like in humans. So it's it's something that people are interested in exploring, but it's a little bit hard to get a grasp on what's actually going on there. Hello, I'm here. This is Z. I think let me see. I'll type in. Don't know if he can get in. Well, anyways, so there's a lot to think about with that paper. It's relatively short, but it's got some interesting concepts in it. Jesse, do you have any other thoughts about the paper? Okay, yeah. Well, I hope going over it twice is probably good to kind of just see it twice, see it 2 times and see how it just to give you to think about it a little bit more. But we'll think about it in the coming weeks. And Jesse, if you find anything inspiring about these 2 presentations, you can bring them up in your presentation. That's scheduled for next week. But it's up to I think you probably have a lot with the paper that you have. So, but
I'm sorry, I will just quickly switch to the computer so that I can, it would be more comfortable. It would just take 1 minute.
Okay.
I'll be right back.
All right.
Okay?
All right. Okay. Okay.
All right.
You're back. And I think Z is coming in as well.
Mm-hmm. Yeah, you can see that.
Once we get back, we'll. All right, there he is. Can you hear me, Z? Okay, good. All right, so now that we're back, why don't we go to the board and talk about that a little bit? So let's see. Here's the.
Yeah, I also had one question to the paper. So about I guess it was in the last graphics that we talked about. There was some kind of 2D raster with this balance and so inhibitory and kind of, I don't know how to call it. So basically this balance heat map, I would say, and it was rastered on some 2D space. So my question namely was what this 2D space was. Was it some kind of brain of a particular organism, or was it some kind of simulated neural network?
So you mean this space, right?
So
do you mean this space? Or question? Sorry.
Yeah, exactly. So it was some kind of 2-dimensional space there, basically where dots were present, dots were painted exactly. So I'm in the space, yes, in this case.
Okay, so it's just multi-dimensional scaling. So the researcher had the structural distance and dynamical difference between all motifs, right? And then they just use, and it's like a space, like say Cartesian space, and each motif is a and the distance between 2 dots is the dynamical distance. So for this chart, and for this chart, the distance between 2 dots is the structural distance, and that's it. So they just use the distances between the motif classes and to form a car business space that represents the relative distance of those dots, those motives. Yeah. Yes.
So once again, all of these dots are motive classes.
Techniques.
Yeah, yeah.
And what's the difference between between left side and right side? Okay, so that's one is the structural mapping, and the other is dynamical classes, right? Do I get it right? Okay, then it's clear. Yeah.
Right.
And so it's the set of all possible classes we can imagine ourselves, or what? Or is it some kind of
it is
classes still relative to some exact?
All possible. I would say it is all possible topologically identical. It's just all possible permutations of topologically identical neurons.
Okay. Then yeah.
Okay.
That's cool. Thank you.
Yeah.
Mm-hmm.
Yeah. Okay, so let's see. Let's move to the board. I've got this is the repo link in the chat. And if we move to the repo and we go to the projects tab and we click on the project group meetings review, and then we have our tasks here, and we'll go from right to left, so done to do, and then we'll go through these, and then we'll maybe recommend some new tasks for the upcoming weeks. So first of all, I should say to Stefan, I have to do your evaluation the next week. So you'll be all right. You'll do fine on that. But I'm just letting you know. I think you have a deadline on your end too. But we'll do. Typically I'll do a review, and then I'll say where you can improve and where you've done well, and so I'll just kind of set up for the next phase of the project in that. But that's nothing to worry about. But just be on the lookout for feedback.
Yeah, sure.
Yeah. So, all right. So done. We've exchanged proposals. So we all looked at each other's proposals. Stefan got in touch with the SimBrain developers. We worked on presentations, and actually Jesse is still in the pipeline to give his presentation. Although if he doesn't have time next week. I think next week we said that we would do both the paper presentation and project presentation. But if that's not convenient for you, we can talk about that later. But so we've done that. We've gotten set up with Jupyter notebooks or some other type of notebook. My other group is using more machine learning friendly notebooks. Such as Colab and Kaggle kernels. So, they find those to be better for their purposes. But I think Jupyter notebooks are fine for what we're doing. Set up presentation schedule, we've done that. Set up programming environments, we've pretty much done that. So then we go to in progress. Present papers, issue number 7. We're in the progress of that, and Jesse's going to give his presentation next week. So we're all coming along with that. Sharing resources and implementation ideas. Looks like, we're just kind of playing that by ear. So when we have things we want to share, or we can always share things in Slack or on GitHub. So Stefan has actually created a Trello board with tasks, and he's been populating that. And is there anything you want to say about the Trello board? Do you have things that need to be brought to my attention, or anything pressing?
Yeah, well, I guess in some cards I've added your name or you as a collaborator, and I've also written there something. So basically, I've made some decisions that may be worth your attention. On the project, you could just look into the Trello board. Also, it's not that urgent, so it's can be done later. But yeah, there is some stuff to discuss basically.
Okay, I think there was one thing about like a two-stage. Can't remember what it was. Something about the two stages of, like, we were talking about kind of like how it resembled tournament selection, but it wasn't tournament selection, at least not the way people think about it. So, what are your thoughts about that issue?
You mean what do I think about this issue?
So yeah, you just presented something. Well, you presented your approach to this problem. So could you talk about it a little bit?
Okay, yeah, sure. So basically, like the whole main problem with the grammar encoding and grammar approach, it's perfectly scalable, at least in theory. Let's look how it will work out in reality. And it's also like it allows us to synthesize some very different size networks, right? So we don't have this restriction that our network would be just like 10 or 5 or 6 nodes big and not more, not less. Otherwise, we kind of won't be able to either scale it or represent it with a bit string of fixed length, but for various lengths. And so grammar approach, it also allows us, at least theoretically, to represent different size, different length networks with the same size string binarily, and so also evolve kind of different size networks. What we would expect maybe naturally to occur, that we have some different size brains. Somebody has 3 neurons more, somebody 3 neurons less, and it's all cool. But the problem with grammar rules approach to the building the networks is that we kind of have to have grammar rules first to be able to work on them. So we will need to have to be able to say, okay, so the letter A stands for this or that matrix, this or that connectivity matrix, and we come to the point where we work with already patterns that are already there. So we have to have some connectivity patterns to declare them as grammar rules, and only then we can use these grammar rules to kind of synthesize new networks and do stuff on them. So the question followed for me, where do we get this grammar rules? Where do we get these connectivity patterns that we can later say, okay, that's our initial grammar rules, and we will work with them. First, of course, you can think about maybe just declaring some random pieces of matrices, or maybe some small random matrices as some kind of initial grammar rules. But, well, this approach, it could be interesting, but it doesn't really have any biological reasoning. And I mean, also stuff here, I think a big thing here is that we are working with weighted networks now. So basically network with double numbers, right? And if we come to the point where we say, okay, for instance, we want 3 to 3 matrix to be our initial grammar rule. Yeah, so all of our grammar rules would be 3 to 3 matrices with some double numbers between 0 and 1 inside them, and with the constraint that each node has, each node has normalized weights. Even though we have these constraints that each node has normalized weights, it's still a lot of stuff and a lot of possibilities, even for this small 3 to 3 matrices, to have some different numbers and some different weights coming from each node and going to each node. And so the approach that I thought would be better to this is to say, okay, so we basically, at the first step, before the grammar rule approach, we just work with matrices of fixed size, let's say 3 to 3. And we try various things out, and we would do it with the same genetic algorithm. And then we will take these networks, 3 to 3 networks, that will prove themselves to be the most fittest, as grammar rules in the next round, where we just use them as grammar rules as some patterns that are also, widespread and fit in by all means. And then we will work with these patterns to generate some bigger matrices. And so we basically use matrices or some connectivity patterns that we found out to be the best ones in their league. So on their size, on their we make the first run. The first step that I called first step is just networks of the same size, of fixed size, that will be represented by adjacency matrix, but it's just a technical detail. The point of it is that all of the vehicles at this stage, they have the same size of the brain, and we pick the fittest brain, so to say. And then we say, okay, this brain that we've picked, or this number of brains that we've picked of this fixed size, they are going to the most fittest ones, the ones that have survived and outbested all of the other. They would be our building blocks to synthesize some bigger networks in the second step. And we would do synthesizing these bigger blocks or bigger networks, bigger brains by using grammar rules approach. And then we overcome this problem that we didn't have initial grammar rules, because now we will have initial grammar rules that would be the best connectivity patterns that prove themselves to be the most finest and the best ones in the first step. And it will also have some kind of biological or at least evolutionary reasoning, because then we don't just take some random grammar rules and see what happens, but instead of this we take some predefined fit patterns, which we say, okay, so if these patterns are fit, they maybe propagate themselves well in the evolutionary timeline where brains become bigger.
Well, also it solves your problem of innateness. So, a lot of people don't really know, but there's this argument that there are innate behaviors that organisms have. Could be stereotypical movement patterns, or could be even in humans, do we have innate language capabilities or not? So, it's there is this sort of chicken and egg question where, we have things that have evolved, but they didn't come from nowhere. So how did they get there if they're not, how do you get an innate pattern if it's not it's just, we don't really know the origin of that. So the origins are always a problem. I think this sounds like a pretty good way around that, at least something that could be suitable, for implementing, on a computer. So, yeah, that's good. I'm glad that you've been thinking about this. It sounds like it'll be, well, we'll have to see, as you go along, whether it'll bear fruit, but we'll see. So I'll look over the Trello board and give you feedback on. I think I've given you my feedback on this for now, but we'll keep talking about it. So then number 16, pick an initial network type. So that's actually for Stefan and for Ziyi, because they both had mentioned this issue. So Stefan has kind of given his thoughts about it. Ziyi, we were discussing this a week and a half ago, maybe. Have you made more progress in terms of implementing your network? Do you have an update on that for us?
Yes, yeah. I was building the association parts of the network this week, and it is a very. I just used outputs of the olfactory system that I built. That is the Lee Hopford network. The outputs of the network that I built as the inputs to the association network. And currently, I'm using the raw gas saturation inputs, gas saturation stimuli as the input to the association network. and it is associating very well. So I can probably share my screen again to see the So so here the two I highlighted. So that is ideal olfactory gustatory inputs, and that is actual the association network outputs. So I guess and that is the weight matrix that maps the olfactory processed olfactory values to the gustatory values. So currently, I guess it's actually associating something, which is nice. So I'm going to try. Firstly, I'm going to try on larger. I'm going to try on different, dimensions of olfactory gustatory inputs, and also I'm going to try on some more complicated cases, and then I'll move on to. So currently, it is static simulation. So then I will move on to the Braitenberg vehicle that is a moving agent, and to see if it is also associating things. And then after that will be visualization and optimization.
Looks good, yeah. And I like the fact that you have results that look pretty good already. So, yeah. So, are there any next?
Yeah. So one thing I am sorry. Yeah. So currently the Lee Hopfield network. So according to the original paper and also according to the anatomy of the olfactory bulb, the mitral cells is the output of the olfactory bulb, and in Lee Hopfield network, it is basically producing the output. But the output is like oscillation. So oscillation over time. So I just use the power of signals. That is just the broad idea from the signal processing. I just do the integration and use the power of signal as the input to the association network. I'm just wondering if that is, a good approach or not.
Yeah, I think so. I mean, you mean you're using something like you're basically calculating a summary statistic of the outputs, and you're using that. Am I understanding that?
Mm-hmm.
Okay. I mean, that's fine. I mean, like we had the discussion about neural
coding.
Yes. Yeah. So I mean, I don't know how the brain really does it, but I mean, if it works, I think it's probably worth trying it, and if it works well, maybe that's a discovery. Maybe because I mean, people in that literature, they've tried all sorts of different transforms. Like some people think that the brain, synthesizes. There's something called multisensory integration where things, are brought together. Signal, from different sensory systems are brought together, and then they're weighted and they're prioritized, and then people use different mathematical transforms to represent what that might look like. So I mean, people have tried different things like that, and maybe the brain is doing some sort of compression or finding like the power spectrum or something, but it's probably wide open. I would. That looks good though. So Jesse, do you have any thoughts about that, or do you have any issues?
So it's sort of. Yeah, I'm just wondering for this sort of raw oscillatory outputs that Lee Hopfield network provides.
Yeah.
Is there any better approach to do with that sort of oscillatory, stuff?
Yeah.
Rather than just use the statistics.
Well, people have done stuff. Yeah, oscillatory thing. Okay. I think with oscillatory stuff, a lot of people have done and this is a little bit far from where you are, but they record EEG, which is a recording of the brain's electrical activity, and they summarize it in terms of looking at the different bands that are emitted.
Yes.
So it's they classify these bands, and they're supposed to represent different states of the brain. So alpha band or beta band, and then they have different frequencies and sort of they've sort of associated with different things being awake or paying attention. I don't know if that would be suitable for your needs, but I think for now just stick with what you're doing, and then maybe when we get a little bit more clarity on what the data look like or what the pseudo data look like, or because you're doing a simulation, I think we'll get a little bit better handle on it. He dropped off, but that's okay. So Jesse, you didn't hear everything that Z had to say. Okay, caught the end of it. Yeah, it was a pretty interesting result. So yeah, I mean, he can probably share that with you. Yeah, we'll see it in subsequent weeks. Oh, he was able to take two sensory. He's simulating two sensory inputs, and he's bringing them together, and he's finding he's basically finding I don't know, you could call it a power spectrum, but he's basically taking the signals and using a mathematical transform to find the, what's going on there. Yeah. Okay. But did you have any other thoughts on, for what you wanted to do, or I'm talking to Jesse. I mean, you can always talk to me offline, but I just want to know if there was something that you wanted to bring up. Okay, that's fine. So yeah, we'll talk more in Slack. Why don't we go through this board a little bit quicker here? So then number 17, conference funding. I've still to hear back from Malin about that, but we'll work on that. Finding data set references, that's in progress. Research potential issues with building block method, that's sort of in progress. We kind of talked about that. That's not pressing. And then work on binary encoding, that was just a general thing, but that was focused towards Stefan. And we kind of discussed a little bit about that. Then Z, review components of models. So we're he gave us this nice result that he showed, and then so we'll keep doing that sort of thing. Review Holland's paradigm, that was Stefan and Jesse. I don't know. That seems to be, on hold, or we'll talk about that later. Then the community evaluation. So I think Stefan was interested in that. Now, I mean, you're talking about a broader community, right? Of people because I was thinking you could get maybe some feedback from the OpenWorm people, because we have people in that community who might be, sort of at the ready to give advice, but you're not really in that group. So, I mean, I can arrange it. So it's
yeah, maybe we can do it. I mean, just I've thought about it also that right now it's more or less the basic Braitenberg simulation, right? So as we are used to see, I honestly whether it's worth spending people's time. What I've thought about to just see how Braitenberg Vehicles. So maybe we can think about doing it at some later stage where I've connected at least network, or I've at least have like the whole pipeline going.
Yeah.
Yeah, and then somehow just give it to evaluation. But I mean, it's not for the current state, because I would say current state doesn't have like something scientific to boast.
Right. I mean, yeah. I mean, the question is, when do you want to get feedback on it? I mean, it's like if you're at an early stage, you might get a little feedback, but if you're at a later stage, people can see more of the value in it. I'll leave that. We'll talk about that in future meetings. So, again, are there any issues that people want to put on the board right now, or any issues you can think of in the next week or two that'll be coming up? No. Jesse or Z? Okay. All right. Yeah. So, I mean, again, you're welcome to put them on the board or maybe bring them up in Slack. So, well, we've come to the end of our hour. Thank you for attending. I know the technical difficulties were significant today, but that's okay. It's just the way it goes in these meetings. So thank you for attending. And next week we'll have Jesse who'll present on his paper, maybe his project. And also, congratulations to Jesse for his diploma. I saw him on Twitter. He got his diploma in the mail, so that was very nice. Yeah.
Oh, yeah. Congratulations, Jesse.
Yeah, it's always good to have like a milestone completed. So, all right. So thanks for attending, and to catch you on Slack and talk to you next week.